If you can't score it, you can't ship it. By the end, you will know how to turn raw agent call logs into a simple, actionable scorecard that highlights broken tools, retry storms, and budgeted success. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. This is what we will build: an agent eval metrics report. Agents talk to tools. Tools fail sometimes. That failure can hide in retries, slow down responses, and ruin user trust. Agent Eval Scorecard is a small, practical way to measure that behavior. It converts tool calls and outcomes into a few crisp metrics. Those metrics tell you which tools to fix first and whether your agent is wasting tokens retrying the same thing. This matters whether you are testing with 10 simulated tasks or a few thousand real requests in production. The basic idea is intuitive. Start with raw logs of tool calls. Each entry records which task, which tool, and whether the call succeeded. From that, you compute a baseline success rate, average retries per task, which tool is most reliable, whether tasks succeed within a fixed retry budget, and finally a fused score that summarizes overall health. Strengths: quick to compute, easy to compare across runs. Weakness: it abstracts away semantic correctness of results, focusing on call-level reliability. We will build a tiny scorecard that reads a toy log and reports those 5 metrics. It is a pragmatic bridge between raw traces and release decisions. You will see how one clear number helps you compare prompt variants or model updates without guessing. Next, we compute a baseline success metric. Now we measure raw success rate. This snippet measures a simple baseline: how often tool calls succeed. The variable calls stores compact task definitions with attempts and a parallel list of booleans for outcomes. The list comprehension builds logs as small dictionaries that include task, tool, attempt number, and a success flag. The variable OK rate then divides the count of successful entries by the total calls to produce a deterministic fraction. This minimal baseline gives you a crisp starting point for comparing future agent changes. The printed success rate shows whether tools are reliably invoked and is the first red flag if production behavior drifts. Next, we look for retry pressure in the trace. This example gauges how much retry pressure your agent exerts. First, the logs are sorted by task and attempt, so related calls are adjacent and ordered. The function groupby clusters entries by the task field, yielding one group per task that we convert to a list. The list length -1 gives the retry count for that task, because the first attempt is free and the remainder are retries. The variable avg retries averages those counts across tasks, exposing hidden loops that waste tokens and latency. The printed average highlights whether your agent is skating by or spinning in costly retry cycles. Now we compare tools to find the most and least reliable. This code compares tools to reveal which one behaves most reliably. The variable stats is a small accumulator mapping a tool name to a pair of successes and total calls. The loop over logs increments total for each call and adds 1 to successes when the OK field is true. The expression with max chooses the tool whose successes divided by total yields the highest success rate. This ranking step surfaces brittle tools that inflate retries and cause silent production failures. The printed best tool helps you prioritize debugging or route strategies around reliable components, while quarantining the flaky ones. Next, we check whether tasks succeed within a fixed retry budget. This snippet turns retries into a concrete service level check. Did a task succeed within K retries? The variable K is the budget. while suck within collects binary outcomes per task. For each task group from groupby, the code lists attempts and finds the first index where OK is true. If that index exists and is within the allowed budget, the task counts as successful within constraints. The variable rate k then averages these successes across tasks, giving a budget-aware success rate. Increasing k typically raises rate k by allowing more recovery, but it may hide latency costs. The printed rate shows pragmatic, bounded success. Finally, we fuse the pieces into one comparable score. This code fuses your metrics into a concise, comparable score. The variable w holds weights prioritizing tool call correctness, budgeted task success, and a penalty for retries. The expression for score multiplies OK rate, rate k, and average retries by their respective weights, then sums them into a single number. The name identifies the configuration, so you can track experiments and compare runs over time. Adjusting weights shifts emphasis. Raising the retry penalty lowers scores for looping agents, while boosting the fast weight rewards within budget completions. The printed run score is a tiny, reproducible baseline for ranking model and prompt variants. This toy flow maps cleanly to a production test. Replace the small log list with your actual request traces. Use the same metrics to gate releases, to select routing rules, or to prioritize tool fixes. The core code does not depend on a model library, so it is easy to run in CI or in a small observability job. Recap: what it is, when to use it, one caveat. It is a compact scorecard from tool call logs that reports success rate, retry burden, tool rankings, budgeted success, and a fused score. Use it when you need a quick, repeatable signal to compare agent variance, or when tool reliability affects user latency. Caveat: it measures call level reliability, not semantic correctness of tool outputs. Next step: tune the fusion weights to reflect your priorities. For example, increase the retry penalty if latency is the highest concern. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.